So welcome, thank you all for coming. First off, my name is Charles Knott, so I'm a new assistant professor here starting August 1st actually in ecosystem-based forest management. And within that, I'm happy to have as a visiting guest here Raphael Chavardes, and also David Anderson is with us. Raphael is a PhD candidate at UBC in the Department of Forest and Conservation Sciences, and he's based in the Tree Ring Lab. And he's working with Laurie Daniels and Dave Anderson as part of the Healthy Landscapes program. So today, Raphael is going to talk to us about fire and climate associations. And with that, I'll give you the floor, Raphael. Looking forward to your talk.
Thank you very much. Hi, folks online, and thank you very much for being here as well. I'd also like just to mention that NSERC and MyTax help fund this on top of those organizations, which have been very supportive over the years. And I also would like to mention that Bianca Askansen and Zev Gadalov are my committee. So today we'll be looking at fire synchrony as climatic drivers in the Southern Cordillera. But first I'd like to clarify what I mean about the Southern Cordillera. Here in the dashed lines is an area approximately 350,000 square kilometers, and it covers much of the montane Cordillera ecozone in both British Columbia and western forests of Alberta. If we look at the fire seasons in 2003 and 2017, there's evident fire synchrony on those images, simultaneous fires burning at different locations. And if we look at a close-up of the town of Wiliams Lake, we notice that those fires 2017 are threatening the community. Those two fire seasons led to the evacuation of tens of thousands of people.
When I go to the site, there's no images. What's the web address?
So if we look at fire synchrony in 2018, we notice, and these are images for August 10th, we notice many active fires across the Southern Cordillera, many of them threatening communities. And the right-hand image is showing us the fuel fire danger index, which is a composite of three things: the ease of igniting the vegetation, the difficulty in controlling the fire, and the amount of fire damage or severity. Now that period of fire synchrony was following a period of intense drought, so basically persistent dry and warm weather. Now when we're looking at this type of scenario, when there's multiple fires and there are some of them large fires close to communities, it becomes very difficult for fire suppression organizations to deploy on the landscape at these different sites. Resources are spread thin and it becomes quite expensive. And some of those, here's an evidence of a tragic image showing a fire with severe impacts entering into the wildland urban interface and taking down some homes. But that's not all. Here in the top left image, we have what we call the formation of hydrophobic soils. So these soils are now water repellent. The organics in the soils are heated up and they turn, there's a waxy coating that's formed, and instead of water infiltrating into the soil, it'll thereafter just run overland and lead to flooding. The middle photograph at the bottom is showing us the result of a mudslide on quite a large roadway. And following high-severity fire, likewise, you'll have the root cohesion, which will be decreased due to the higher severity fires that takes down the vegetation. So there's a loss of cohesion, and following a precipitation event, the soils can be thereafter mobilized in the form of landslides or mudslides. And as a consequence, you can have decreased water quality. This is a picture by NASA taken on August 21st, 2018, so it was this year. We can't even see Vancouver there under that pall of smoke. All those valleys in the interior are choked with smoke. We're talking about many communities and even cities with millions of people that are being choked by smoke. And I just heard that Edmonton was also pretty badly hit this year. So what does this mean for people who are having health issues with regards to this smoke? Now, of course, many of you know that fire plays an important ecological role in sustaining forest diversity. But when we're looking at fire synchrony, it's becoming a societal issue. So we need to learn more about this. So for this research, what we looked into was whether these fires are historically unprecedented, or whether this is the impact of recent climate change. More specifically, we posed the following first question: was fire synchrony historically common in the southern Cordillera? And two, if it was common, what were the climatic conditions that were associated with fire synchrony? Now I'll show you why this research is quite novel compared to other research that has been done with fire climate associations. First of all, we're using fire scar records. So in the field, this is how a tree looks like. There's a Douglas fir on the left and a lodgepole pine on the right, and they've been multi-scarred. And once we extract the sample from the field, we bring it back to the lab. We sand it to progressively finer grit until it's almost a shiny polish. Then we scan that sample at high resolution. We measure each one of those growth rings. And then we use a statistical technique known as cross-dating to identify the pattern of wide and narrow rings over time. And by matching that pattern with a master chronology of the area for that particular species, we're able to identify when each one of those rings was formed, those annual growth rings. And by doing that, we're also able to place an exact calendar year to each one of those fire scar years. So in this research, we had 1,886 samples. We're able to get an annual resolution for those fire scar years. And given that these trees are able to live for many centuries, we actually have multi-century records of fires. Now, fire scars are an indication of a range of fire severity. They are predominantly formed by low-severity surface fires, but they can also form at the edge of higher severity fires, where the intensity of the fire drops. Now, for this research right here, fire synchrony was defined as follows: as when fires were burning at multiple sites within the same year. And here are the 17 sites from which we extracted those fire scar samples. Now, this research presents the work of many people in the US Forest Service via Emily Herdal, also Canadian scientists at the University of Victoria, University of British Columbia, and the University of Guelph. There are also people in Parks Canada, such as Rick Kubian and Jed Cochran. But a lot of this work has been predominantly done by Dr. Lori Daniels. She was on the committee of many of these students, or has directly supervised these students, or has directly done this research. Now, one of the interesting things as well to notice about this is that the sites are placed in different eco-provinces across the southern Cordillera. From the southern interior, the southern interior mountains, and also a combination of two eco-provinces, the western Alberta upland and southern interior mountains in the northeast, to represent sites on the eastern side of the continental divide. And here are the range of ecosystems that we're looking at. You've got some interior Douglas fir, ponderosa pine into interior Douglas fir in the central interior and southern interior respectively. But then we also have a whole gradient in the southern interior mountains from ponderosa pine all the way into mountain spruce. And east of the continental divide, we have mountain spruce and upper foothills. Notice in yellow, those are all the different species that are being represented by the fire scars. You have Douglas fir, ponderosa pine, but also western larch, lodgepole pine, and hybrid spruce. So this is where this study is novel. We're really getting at this mesoscale analysis of fire history. It's been done a lot at a local scale, or in USA has been done at a mesoscale too. But for Canada, this is new. This hasn't been done. Here we have the fire chart for one site only, and this is the work that has been done in Jasper. So I studied fire history in Jasper National Park for my MSc. So here I'm just presenting the fire chart for that site. Altogether, there are 45 horizontal lines. Each one of those is representing the fire record for one plot, so the 45 plots. And each one of those vertical gray ticks is representing a fire year. And now the criteria for a fire year were 2 or more dated fire scars at 1 or more plots, because we're looking at a spatial process, fire. And if you look at the bottom of this graph, look at the change. Right here, we have the site level record. Now, all we're doing is collapsing all of those plot data, the 45 horizontal lines, into that one horizontal line. Here, the record is for 2 or more samples. So clearly, it's going from 1701 to 2000, but it went further back in time, but we just clipped it this way just to simplify the visual aspect of this chart. Each one of those red vertical ticks is a fire year, where the criteria for that were 2 or more dated fire scars at the site. The vertical black ticks, on the other hand, were widespread fire years. They're representing more extensive evidence, and the criteria for that were 10% or more dated fire scars at the site. Now again, if we look at that one green box at the bottom, there it is again, at the very bottom. So that's the one site for Jasper, but then there's another 16 sites above. And that same process with collapsing that data from the plots into the site was done for each one of those lines. Some sites had 120 plots. So this is a really rich data set. That's pretty much the point that I'm trying to tell you here. Now again, what we did here, we collapsed all that data onto that one panel at the bottom. And we're going to look at it a little bit bigger here. So that's that regional fire record. Here it is. So on the vertical axis, we have the number of sites with a fire year. And we have two types of columns. We have red columns and black columns. The red columns are basically just adding up all the red vertical ticks. The black columns are adding all the black vertical ticks. So for fire years and widespread fire years over time. That's what it's showing us. And we decided as a criteria that synchrony would be when there's evidence of fire at more than 20% of the sites. So whenever each one of those red or black vertical columns is entering into that gray box, we have fire synchrony. So fire synchrony for the red columns or widespread fire synchrony for the black columns. Here, just underneath the graph, and it was emphasized by going underneath the horizontal line, there are blue ticks, and they're representing the non-fire years. There is no evidence of fire at the recording sites. And this one curve here is showing us the number of recording fire scar samples. In other words, the sample depth over time. Now, things are not always easy. And there's some confounding factors that we can look at, that we can look into over the 20th century. First of all, there's strong evidence of fire exclusion at the turn of the 20th century in the documentary records. So basically, First Nation peoples, people of dual ancestries, and also homesteaders who were living in the area were effectively told that you cannot use fire as a land and resource management tool. So that effectively removed fire as a land, as a tool on the landscape, and its activity was thereafter decreased. But there was also fire suppression after 1945. So following 1945, fire suppression organization adopted a military command structure. They also adopted aviation as well as mechanization. In the 1970s onwards, there was also the use of satellite technology and heli attack crews that were very efficient at suppressing fires before they reached 1 hectare in size. Finally, in the scientific literature, with regards to climatic variation, between 1946 and 1976, there was a low northeastern Pacific sea surface temperatures which were found. So these 3 confounding factors led us to decide to omit that period for the fire climate associations that I'll be presenting to you later on. Likewise, if you look at the early part of the record, there's a few issues. First of all, I had to use some climate reconstructions. I'll be presenting these to you in a few slides. But basically, for precipitation, that one climate reconstruction only started in 1746 for Cranbrook, which was in the southern Cordillera. So it didn't represent the common interval of time prior to 1746. So that was a first problem. And the second problem, you'll notice lower sample depth in the early part of the record. So we also omitted that part of the record. And so all of the fire climate associations that I'll be presenting to you is from this one figure. from 1746 to 1945. It's a neat 200-year period. We'll get back to this figure afterwards with the latter part of the record after 1945, because there was something very important about that figure too. What do we notice? Let's look at some descriptive statistics. If we were to count each one of those red vertical columns entering into that gray area, there's 50 years with fire synchrony. And if we count the black columns here, there's 6 of them. Here there's 1758, 1768, 1831. Oops, sorry, 1831 is here. 1847, 1869, and 1889. So sorry, that one was not in. So there's just those 6 years right there. I'm just going to erase that. So now you know that there's those 6 years. They were basically the black columns that were going up into that gray box. Now what do we have? So more descriptive statistics. Fire synchrony, on average, happened once every 4 years, and the range of fire-to-fire intervals was between 1 to 15 years. If we're looking at widespread fire synchrony, on average, 1 every 26 years, and the range was between every 10 to 63 years. Is that okay? Oh, sorry. Thank you. And then, these are the images for the widespread fire synchrony. So again, those years are 1758, 1768, 1831, 1847, 1869, and 1889. The white dots are symbolizing where there's no evidence of fire. The red dots, evidence of fire, and the black dots, evidence of widespread fire. Note that there's some equal provinces where there's no evidence of fire, even if there's a widespread fire synchrony. So in 1758 and 1768, east of the Continental Divide, and in 1889, in the central interior. So that answered that part of the question. There was some fire synchrony historically. Now, if we look at the fire climate associations, first of all, one note about the climate reconstructions. Unfortunately, instrumental records don't extend that far back, right? They often go back to the 20th century, sometimes before, but rarely. Oftentimes, it's more like in the mid-1900s. With tree rings, though, tree ring proxies, we are able to reconstruct climate prior to the instrumental record. And here at the bottom, we have the drought index from 1746 to 1946. Drier valleys are below the axis, wetter valleys are above the axis. In this case, we use 3 types of reconstructions. The Palmer Drought Severity Index for summer, so we just label it drought here, and it's a combination of both precipitation and temperature. And then we had reconstruction for precipitation, and it was pretty much the rainfall prior and snowfall prior to peak fire season, from previous July to current June, and then temperature for the summer, or late spring to summer, from May to August. And here they are. So drought at the top, precipitation at the center, and temperature at the bottom. Now, each one of those blue circles is showing you the non-fire year. There's 14 of those years, and they're predominantly above the line with drought and precipitation, meaning generally wetter conditions, and below the line for temperature, generally cooler conditions. The widespread fire synchrony were the black points, and they're generally below for drought and precipitation, so drier conditions, as you would expect, and above the temperature for the temperature reconstruction, meaning warmer conditions. For fire synchrony, there's much more variability above and below the line, but they're generally during drier and warmer conditions, as you would expect. Now, this is a descriptive way of looking at the data, but we can also use some inferential statistics. So here we're using a type of analysis. We're trying to determine whether or not the conditions were particular during a given scenario. So here we have the non-fire years with the drought index, wetter values above, drier values below. And each one of these bars is for the average value for year 0. So the non-fire years would be year 0, then the 3 preceding years, year -1, year -2, and year -3. And when they're colored bars, it's showing statistical significance. And what we're finding is that non-fire years were significantly associated with wetter conditions in the current and previous year. And it's a similar story when we're looking at the 3 different reconstructions. Non-fire years were significantly associated with wetter and cooler conditions in the current and previous year, or previous year. But the story is different. Oh my gosh, sorry. Sorry about that, everybody. It's because I clicked on the keyboard. That's why. So I cannot use the keyboard. I will just have to use the pointer. There we go. Thank you so much for your patience. You're a great public, everyone. But the situations are completely flipped during when there's fire synchrony. Basically, conditions were significantly drier and warmer in the current and or previous year. When there's widespread fire synchrony, the average values are quite drier and warmer, and the associations were for the current year. But again, that's for only 6 years, so the confidence intervals were quite narrow in this case. And I can show you the actual confidence intervals if somebody asks me that questions at the end. They want to know more about this type of analysis. Now that was really interesting to look at that at the regional scale, but we've got some really neat spatial networks of drought and precipitation for the southern Cordillera. So now I'll be showing you a bunch of maps, not too many, but some really cool ones. As you would expect, during non-fire years, the conditions were wet to extremely wet in the southern Cordillera. But when we had fire synchrony or widespread fire synchrony, they were near normal to extremely dry conditions. And notice the pattern of the north to south gradients during the years with fire synchrony and the east to west gradients during widespread fire synchrony. So this probably has to do with the placement of pressure systems. More in detail, in the years with widespread fire synchrony, you'll notice near normal to dry conditions. But in some cases, sometimes you might have incipient wet conditions. But this is in an area that's relatively dry in the southern interior, for this one black dot there. But you also notice that there's in some cases, there's no evidence of fires, even if there's drought. So drought doesn't necessarily guarantee fire. And that's quite obvious here in 1889 in the central interior. And in 2017 and 2018, there's lots of fires in the central interior. So there's something to think about there. Maybe it was time for the central interior to burn. I mean, it's been quite a while. So to summarize the results, and then we can look a little bit at some discussion slides, we found that fire synchrony is not unprecedented in the historical record. What we've seen with the fire scar records is that fire synchrony was common, but that widespread fire synchrony was less common. But there was evidence of it. And it's consistent with the recent fires, like in 2003, 2017, 2018. Drought is a strong driver of fire synchrony. Here, all the points below that dashed line are representative of the 35th percentile. And all the black dots for the widespread fire synchrony are below that dashed line. But we're finding that there's some years that didn't show evidence of fire synchrony. So this is one point that needs to be made is, although you may have drought, it doesn't guarantee fire synchrony. Drought is not a sufficient condition. So then apart from drought, what could have happened over the recent fire seasons? First of all, there was a high number of lightning ignitions. Each one of those dots is representing a lightning strike. And when they're larger, they're showing more activity. And in this case, on this tweet, it says, in the past 24 hours, there are 98 new wildfires, the majority being lightning caused. And then if we look at some recent research, they're finding in the northern hemisphere that there's going to be increased lightning ignitions due to increased temperatures. Now back to this figure here. Everybody was probably going like, wait, that's so different after 1945. We see decreased fire synchrony, and an increase in the non-fire years. Now remember, this is across 17 sites. So that means that there's considerably less evidence of fire across the southern Cordillera at all these different locations. So in absence of fires, what do you think happened? These are images close to the town of Cranbrook in the southern Rocky Mountain Trench. So these are dry, mixed conifer forests. If you look carefully, you might find a ponderosa pine tree within there, like a bigger, redder tree. Everything else is pretty much Douglas fir. Now, if you go back in time, you might imagine these forests as being more open, more park-like, range-like, and frequent fires burning at the surface, cleaning up a lot of these smaller Douglas fir trees. But then, with fire being removed from the landscape, a lot of these trees persisted in the subcanopy, and now they form ladder fuels. So fires are able to go from the surface, move into the crowns, and what do you think is going to happen if there's an intense drought? It's more likely that there's going to be a higher severity fire. But that's not all, not just in dry mixed conifer forests. Here we have more music forests, and this are in the higher latitude sites. This is in Jasper, in the montane spruce. The top photograph is showing us open and closed canopy forest interspersed with grasslands. And then the bottom photograph is showing us predominantly closed canopy forests. Now in 2003, there was a big burn called the Synchrony Ridge burn, and it was following a period of drought in June. Like normally there's rainfall that would have, mitigated that fire that had occurred early. But if we have the same scenario where we have a fire that is ignited, or fires that are ignited at multiple places with drought, then you might expect a higher severity fire, given the abundance of the fuels here on this landscape. Not only that, but if we're looking at the mountain pine beetle epidemic, and this is only until 2012, it doesn't show how it's more prevalent now, notably in Jasper National Park. In the 1990s and 2010s, just for that picture showing the extent, we find abundant dead fuels on the landscape. And now there's not enough understanding of how the fuels are impacting fire behavior. Some research is showing that the intensity of the fire increases, the fire increases in speed. However, there's also different results. And it's likely due to how the fuels are changing over time, like between a red attack, a green attack, gray attack. But you do have lots of standing fuels, you have lots of ground fuels, and you also have, in this case, lots of seedlings and saplings that are establishing those canopy gaps. Last but not least, and these are prediction models done here at the University of Alberta, but also with Natural Resources Canada. So models are not perfect. They have a degree of uncertainty, but this is done with the best data at the time. And it's showing us an increased or a prolongation of the fire season from 3 to more than 20 days within our study area. And likewise, when we're looking at the severity, we're finding increased fire severity in the study area. So that looks all depressing, but there are also a lot of solutions and a lot of things that we can do. For example, if you're part of a community, or if you would like to talk with your neighbors, or if you're an industrial partner, how do you get to live with fire? How do you get to coexist with fire? Well, you can also, first of all, look at Fire Smart Canada, Firewise in the US, and there's a lot of information that can be gleaned from these sites in order to ensure that your property, as well as your community, is at least in a safer position. It's not absolutely safe, but at least you can take steps that it will mitigate the damage. You can also have a very solid evacuation plan, so you're not basically evacuating without really knowing what you're doing. So it's very important to be prepared and to anticipate some of these things. But there's also lots of interesting literature that's coming out from Nature, Science, relatively recently. So what I said, learning to coexist with wildfire, there's lots of interesting things that are coming out from the literature. And I would recommend any forest or fire managers to be reading these papers. If you don't have access to them, find out if you have any family or some friends who are academics and ask them to share some of these papers with you. Lastly, And this is more of an international endeavor. There's lots of adaptation, mitigation, and transformation solutions from many countries. So this is from the Intergovernmental Panel on Climate Change and the World Meteorological Organization. So we're not alone. We have to work as a team on learning how to adapt to a lot of these problems, how to transform our societies. And on that note, I would like to give my special thanks to the following organizations and people. And I thank you very much for your attention.